Oh man, I took that out of there, didn't I? That's okay. So what I wanted to show you first is, okay, we're combining the last three sections of chapter 6 with the first three sections of chapter 7, and there's a reason for that. At the end of chapter 6, we did that section 6.6, which is about combinations of functions: add, subtract, multiply, divide, and then there was a new operation, which is composition. Right? We learn about composition so that we can fully understand inverse functions, which was the next section. And we learn about inverses so that we can understand the graph of the radical, the square root function, as being the inverse of a quadratic. Right? Taking the square root and the square, those are inverses of each other. So we would expect that their graphs are flips across the line y equals x, the identity function. Right? We learn about these things together for a reason. So here's the graph of y equals the square root of x, and then this is 1/2 of the graph of y equals x squared. Right? It's not the whole parabola. It's only the part that goes from here and to the right. Because it's got to be that these two graphs look like this line is a line of symmetry for it. That's what inverses are all about. Okay, these two have to look like they're just flips across that line. Okay, well, the two functions that we have left to cover are also inverses of each other. Right? Today we do exponentials. Next class we do logarithms. Okay, so you're starting to get into sophisticated kind of stuff here. Okay, so there's a lot of, these are all coming from the SOLs, essential learnings. Now the truth is that we've used, these mostly are the objectives that we had for the last lesson when we were learning how to graph square roots. It just here, that very first line, instead of saying recognizing the graphs of radicals, it's saying recognize the graphs of exponential functions. So recognize the graphs and then move them all around, doing all of our adding and subtracting and putting minus signs in front, stretching and compressing and all that. So that's really just a repeat. We've used those for absolute value. We used them for quadratics. We've used them for square roots. Now we're using them for this. But there is one more. There's more to this. And this is the difference between the regular Algebra 2 class and this higher Algebra 2 trig class. We're going to discuss domain and range as we go along. It's an important part of this. It's a part that I know that it's hard for students the first time you see it, but you guys need to be always thinking about domain and range issues. The lower class, you know, I didn't want to complicate it too much. So we will, this is a slide they didn't see. So I do intend to talk about domain and range as we go. Okay, first, when you don't know anything about the graph of a function, you usually plot a few points, see if you can determine what it looks like. All right, so in this case, this is an exponential function. Y equals 2 to the x power. Okay. Why do you think we call that an exponential function? Because the x is in the exponent. When the variable is in the exponent, that's an exponential function. It doesn't have to be just x. It could be a variable expression. It could be x plus 5. You know, it could be x squared minus 3, 2 to the x squared minus 3. That's an exponential function. As long as the variable is in the exponent, it's exponential function. Okay, so I'm going to use a table of values here to start to plot some points. All right, I already filled the x values, 0, 1, 2, 3. Where did those come from? Say again? You get to pick them, right? Remember, the x values, the independent variable, you get to pick. I picked them. Okay, so now we're going to one at a time. We need to plug these values of x into the function and calculate the y. So when x equals 0, what does y equal? 1. Remember, this is the properties of exponents thing. Anything to the 0 power equals 1. Okay, when x equals 1, what does y equal? 2. When x equals 2, what does y equal? 4. When x equals 3, 8. Right, let's plot those 4 points. 0, 1, 1, 2, 2, 4, 3, 8. Okay, what do you think is going to happen when we start plugging in values of x that are less than 0? We can see what the shape of the graph looks like here. What do you think it's going to do when we start going over here? It's going down. Okay, let's see what it does. Okay, let's see, I added another little table of values. X equals -1, -2, -3. What's the value of y when x equals -1? Say again? It's a half. Remember, 2 to the -1, how do you get rid of the negative exponent? You flip it to the denominator, so it's 1/2. And just for the purpose of graphing this, I'm going to write it as a decimal, 0.5. And if you want, I mean, you can do these calculations with your calculator too, right? If you don't want to turn it into a properties of exponents quiz, then put it in the calculator. What is 2 to the -2? It'd be 1 over 2 to the +2, 1 over 2 squared, 1/4, 0.25. What about 2 to the -3? Right? 2 to the 3rd is 8, so this is 1/8, 0.125. Right? So as the x values get less and less, the y values get smaller. Right? What do you think would happen if I put in x equals -4? It would be a 16th, even smaller, right? If I put in to the 5th power, 1/32nd, right? So here's our next 3 points. There, there, and there. Now, what if I make this like 2 to the -100th? Then it's 1 over 2 to the 100th. Does that equal 0? Is there anything I could plug in for x that would make that fraction equal 0? No, there isn't, right? Because if you're going to flip it to the denominator, what's in the numerator? 1, right? If a fraction equals 0, it's because the numerator equals 0. And our numerator is 1. What it means is that this graph can get infinitely close to the x-axis, but it can never touch because y cannot equal 0. It cannot equal 0. So you got to draw these graphs like this. You got to make it go right along the x-axis to make it look like it's never touching. Something like that. Okay. Now, just looking at that graph, again, here's where this differs for you guys a little bit, but what would you think is the domain of that function? Yeah, all real numbers. I mean, again, when you look at that, we're good with polynomials now, and we know that we can't divide by 0 or take the square root of a negative. For an exponential like this, again, the only thing that you care about is there's something I would plug in for x that would make y undefined, and there's not. This thing, you can plug in any value of x. Y is always defined, so you say all reals. Okay, what do you think the range would be? Yeah, again, it's not like the square root where y could actually equal 0. Then it was y greater than or equal to 0. This one is never going to touch the x-axis, so you have to say y greater than 0. Okay. Okay, that was y equals 2 to the x. The next one will be, if we're ready, y equals 1/2 to the x. Okay, here's our table of values. Let's start plugging in some x values to calculate the y so then we can plot the points. Right, when x equals 0, y equals 1. Good. When x equals 1, y equals 1 half. 1 half to the 1, so I'll put 0.5. When x equals 2, 1 half squared, 1/4, 0.25. And what about 1 half to the third? 1/8 or 0.125. Okay, now put in the calculator, what is 1 half to the negative 1? If you need to. 1 half to the negative 1. 2. What is 1 half to the negative 2? 4. What is 1 half to the negative 3? See the pattern there? Do these numbers in the table of value look familiar? They're the same numbers as 2 to the x. They've just flipped across the y-axis. So now when I graph these points, it's 0, 1 is here, but now it's negative 1. I'll go this way. Negative 1 is 2. Negative 2 is 4. Negative 3 is 8. And then these are 1 half, 1/4, and 1/8. And again, the same point as we made on the last slide, there's nothing you can plug in for x that's going to make that the value of y equals 0. There's no way for y to equal 0. So this graph will get infinitely close to the x-axis, but it will never touch. Okay, on both of those, I should have mentioned this on the last slide, but what's the y-intercept? 1, right? When x equals 0, y equals 1. And that was the same for the 2 to the x and to the 1 half to the x. The y-intercept, it's always what you get when you plug in x equals 0. Y int. Okay. So those two functions are two examples of the different kinds of exponential functions. Right? One of them is called exponential growth. Right? Exponential growth is when the graph looks like it's increasing from left to right. And exponential decay is when the graph looks like it's decreasing from left to right. I mean, exponential growth, you can hear that not just in a math or a science class. I mean, you can read that in any old newspaper articles trying to tell you about something that's growing really quickly. They can say, oh, it's growing exponentially. Now, do they really mean this kind of exponential? Maybe not. But they're just trying to get across the point it's growing really fast. Because that's what the graph of an exponential does. Once it gets to the right of x equals 0, it shoots up really fast. The slope is very great. Now, in both of those, whether it's growth or decay, it cannot touch the x-axis. And when there is a line on the graph that your function's graph cannot touch, that's got a name. It's called an asymptote. And so normally when we have an asymptote, we draw it on the graph like a dashed line, and we label it. Y equals 0. Right, so there's the word, asymptote. That's how it's spelled. It's like asymptote. So this is the first time we've really gotten to asymptotes. And we have them for exponentials, we're going to have them for logarithms, and in the next chapter about rational functions, we have them all over the place. Now, what this book is calling the general form of an exponential function is this right here. Y equals a times b to the x, right? So we had 2 to the x and 1/2 to the x. We didn't have a number in front of that, which means the number is 1. Right? If you don't see a number in front of the exponential term, then it's 1. But so it could be multiplied by a constant, and that would still be considered a general form of an exponential function. Okay, the b, whatever is being raised to the power, is always a positive number, and it does not equal 1. Because what kind of function would you have if b equals 1? Because what's 1 to any power? It's always 1, right? So this would be a constant function. It would just be y equals a. So that's for exponential functions, we don't let b equal 1. It's positive, not equal to 1. Okay. If the b is greater than 1, then it's called exponential growth. If the b is less than 1, it's exponential decay. Right? We did 2 examples. The 2 to the x was growth because 2 is greater than 1. We did 1/2 to the x. That was decay because 1/2 is less than 1. Good. Curtis. Okay. Now, what is the effect of the a? If you had a constant in front, what does that do to the graph? Well, in terms of what we already did in the homework, I mean, what does it generally do when you multiply the function by a constant? It's a stretch. Okay, so this is actually, it's a stretch. It's a vertical stretch. You know, and I've graphed it in the calculator. On the first line, I've got the plain old 2 to the x, and that's the thin line right there. Okay, and then on the next line, it's 3 times 2 to the x, and that's a fat line. That's this one right here. And you can see that the fat line is going up faster than the thin line. Right, so that's a vertical stretch. That's what you expect. What is the y-intercept for the 3 times 2 to the x? How about look in the table of values? It's 3. Okay, so in fact, whatever is that number right there, that's the y-intercept. That's the value of the function when x equals 0. Right? Because if I plugged in x equals 0, then 2 to the 0 is 1, and 1 times 3 is 3. So actually, this number right here is the y-intercept. Right. So if you don't see a number multiplying the exponential term, then the y-intercept is 1. That's why the 2 to the x, 1/2 to the x, both of them had a y-intercept of 1. If you're multiplying by a number, y-intercept is whatever that number is, 3. Did multiplying by a constant change the domain or the range? I mean, if you could plug in all real numbers before, can you still plug in all real numbers? Yeah. Did it change the range? I mean, just look at the graph. You know, it's still, there's nothing we can do to plug it in to make 2 to the x equals 0. So 3 times 2 to the x can't be 0 either. So it gets infinitely close, but it never touches. So the domain is all reals. The range is y greater than 0. Okay. So the first kind of problem you got to do in the homework is this. They've given us an exponential function, and they're asking 2 questions. Is it growth or decay? And what is the y-intercept? So how do you tell by looking at these 2 whether or not they're growth or decay? What did we say? If what's bigger than 1? the b, right? Mark's got it. Whatever's being raised to the power, if that's bigger than 1, it's growth. If it's less than 1, it's decay. So tell me on this first one, is it growth or decay? 0.95 is less than 1, decay. How about this one? 2 is greater than 1, growth. Okay, what did we say about the y-intercept? It's the a. So what's the y-intercept of this one? 12. What's the y-intercept of this one? 0.25. Okay, you could just see by looking at it. There's not a lot of work to do with those. Right, so this one was decay, and the y-intercept, again, since the x is 0, it's the 0.012. And this one is b greater than 1 is growth, and since the y-intercept is 0.25, then it's the 0.25. Okay, so here's your first you try that you're going to hand in. Determine growth or decay and y-intercept for both of those. Are you okay, Shizla? You tired? I'm boring you too much? Okay. No, just answer the question. Growth or wake up. I'm doing something. Doesn't take too long, does it? What did you say in the first one, growth or decay? Right. 4 greater than 1, growth. What was the y-intercept? 3. 0, the 0.03. How about the second one, growth or decay? 0.75 less than 1, decay. What's the y-intercept? 11. Okay. Too easy, right? So the thing is, exponential functions are very practical. And you guys are such a young class, so maybe you haven't had as much of this as some other classes might have, unless you're a sophomore or junior. In chemistry class, exponential decay, an example of that is what you call half-lives, right? So a half-life is when you have a radioactive element, right? How long does it take for the amount of that element to become half of what it was? That's called a half-life, and that's an example of exponential decay. If you're in a biology kind of class, maybe you do something like a population growth. Sometimes they're using exponential growth models in some way. If anybody, some of you might have families that have businesses or something like that, and a business at the end of the year, when they do their taxes, they got to take into account the value of their equipment. And generally, you depreciate the value of your equipment. It becomes less valuable every year that you own it. And that would be an example of exponential decay. If you invest money, right, you're earning interest on your money. So it's growing by a certain percent every year. That's exponential growth. So there's a lot of very practical problems that you can do with exponential functions. Right, now this is actually just like a different form of the same function that we saw. Right? We already did this one. We did y equals a times b to the x. Okay, well this one is a little different. Instead of the y, it's got a of t. That's function notation. It's the amount of something as a function of time. The lowercase a is the same. That's still what's different about it now is, besides being the y-intercept, now in a real world problem, the y-intercept, when t equals 0, that's like the beginning time. That's the initial value that you've got. So whatever is at a, that's the initial amount. Right? Because it doesn't make sense if you're talking about time to deal with t equals negative numbers. Right? Time is 0 or positive. So it starts at 0, that's the initial amount, goes to the right. It's still the y-intercept. It is the y-intercept. Okay, now instead of giving us a b, they're giving us 1 plus r. Okay, now if r is a positive number, then when you add 1 plus r, you get a number bigger than 1. That's growth. Right? If r is negative, then 1 minus a number would be less than 1, and that would be decay. And again, instead of x, we're using t. Because it's a real-world problem, and time is the independent variable, then t is what we use. Again, and this a parentheses t, that's function notation, right? Don't think of that like a times t. It's not a times t. It's like saying f of x. A as a function of t. Okay, so modeling exponential growth. You invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? Okay, so let's see. A of t equals a times 1 plus r to the t. Okay, again, what does the lowercase letter a represent? The initial amount. So in this problem, what's the initial amount? $1,000, right? This is going to be the a. And the 1 plus r, remember, the r is the change. If it's positive, then it's a growth rate. If it's a negative, then it's a rate of decay. In this case, the account pays you 5%, so is it growing or decaying? It's growing, right? So this r is going to be 5%. But in a math equation, right, 5% equals 0.05, right? 0.5 is 50%, right? 0.05 is 5%. Remember, 5% means literally 5 per 100. As a decimal, that is 0.05. So when we plug it into that formula, we got to put in 0.05. So here's our function. A equals, edit. A of t equals 1,000 times 1 plus 0.05 to the t. Or A of t equals 1,000 times 1.05 to the t. Right, that is our exponential growth function. Okay. Once you've got the function, how much money will you have in your account after 6 years? What are you expected to do? Say again? Yeah, substitute t equals 6. Right? Just like we do with function notation. When I say find f of 2, means plug in 2 for x. Now we're doing a of 6. So 1,000 times 1.05 to the 6th. And that you can put in the calculator. 13. 1340.10. If you're looking at what somebody else has got on the screen, you're doing the next problem, not the one. Right, 1,000 times 1.05 to the 6th. And usually, because it's money is involved, you're going to round it off dollars and cents. right? $13.40 and 10 cents. You just got $13.40? Let's see. It's because you rounded off. Don't do that. Just put it in. Put in the calculator just like this. 1,000 times 1.05 to the 6. Don't do 1.05 to the 6 and then round that off and multiply by 1,000. Right? The calculator will keep all the significant digits there. Okay, so try to do the same thing with that one. Invest $500 at 3.5% interest and figure out how much money you've got after 5 years. You definitely need to be doing this, because if you just skip in the actual doing of the calculation and it turns out you're not doing something right, you don't want to be the test to be the first time you figure it out. Anybody get an answer? Mark? What? What did you do? It's not, okay, where'd you get this 3.5? Right? It's 1 plus R. And what is R? Come on. Incorrect. What is R? No, it's not. What is R? 0.035. Okay, I just went through that explanation of percents as decimals. Right? Do you get it? Why? I mean, we didn't have one. That was the first one. It's not like, I'm using the examples in the book, but I didn't do the first one. Who's got an answer? Shane has got it. Finally. 593.84. Good job. 593.84. Good. No, you didn't. No, what did you do? No, what are you doing here? No. Okay. Okay, first, what is the value of A? This is the A. What is the value of R? 0.035, right? Move the decimal place over twice. So when you add that in here, this is A of T equals 500 times 1 plus 0.035 to the T. So A of T equals 500 times 1.035 to the T. That's the function. Remember, you were supposed to have mastered decimals, percents and decimals a long time ago. Okay, now how do I find how much is in there after 5 years? Okay, so A of 5 equals 500 times 1.035 to the 5th. Now, with your calculator, watch how I'm doing this. Okay, I'm going to be very frustrated. You see, keep making the same silly mistakes because you can't just enter something exactly the way it's written. Don't do one thing and hit enter and then do another thing and hit enter. You're goofing it up, right? You're goofing it up. Watch. 500 times 1.035 raised to the fifth. How hard is that? Just do it, right? Don't make it into another process and get it wrong. Let me just do exactly what's in front of you. Enter. 593.84. Trying to remember what's next. And when we get to the next examples, you'll see, it's common mistakes that people make with these. Even in my pre-cal, they still make some of the same mistakes. They still have problems with percents, which is a shame, but it happens. Okay, now let's go to now we jump to the next section, 7.2. We already looked at the comparison between 2 to the x and 3 times 2 to the x. What would we expect to be the graph of 1/3 times 2 to the x? What would be the effect of multiplying by that number? It's a what? It's a compression, right? When you multiply by a number less than 1, that is a vertical compression. Okay, and again, what would be the y-intercept then? One-third. It's whatever the a is. The a is 1/3, right? Look at when x is 0, what does y equal? 0.333333, 1/3. Okay. So we've done a stretch and a compression. What is the effect of putting a minus sign in front of the function? It flips it across the x-axis. Okay. So this line here is the y equals 2 to the x. The fat line is y equals negative 2 to the x. So all the y values are negative. Okay, did that change the domain? What is the domain? All real numbers, right? No problem with that. Domain. Come on. All reals. What about the range? Y is less than 0. Now this thing is below the middle, right? It can't touch the x-axis. It's still an asymptote on the x-axis, but it's going down. So y is less than 0, right? And that's specific to this graph right there. Blue. Okay, so what are this is an example from the book. It actually does not ask you to graph it. It just says, how does the graph of negative 1/3 times 3 to the x compare to the graph of the parent function? Okay, well, first off, what do they mean by the parent function? Remember, for all the other functions we had, like absolute value was the absolute value of x. Quadratic was y equals x squared. Square root is y equals the square root of x. But what's the parent function for an exponential? In this case, it's going to change, right? In this case, the parent function is y equals 3 to the x, right? It's an exponential growth and the base is 3. And now at that point, you figure out what does that negative 1/3 do to it. But whatever is the exponential part, that is the parent function part of it. It'll be a little bit different depending on the base. So tell me what's going on, this negative 1/3. What is the negative doing to the graph? Flipping it, and the 1/3? It's a compression. Shrink, compress, whatever one you want. right? So if you look at the graph, right, this is the y equals 3 to the x, right? Still had a y-intercept of 1. It was exponential growth. It had a asymptote on the x-axis. When I flip it, now the y-intercept is negative 1/3, right? Because of that 1/3 which is in front. The asymptote is still here. So now the new range is y less than 0. Okay, describe this one. Just describe. What are the transformations? What is the parent function? What are the transformations? What is the parent function? 5 to the x. Right, it's just the exponential part right there. Y equals 5 to the x. So basically, you got to describe what's going on because of that negative 0.5. What is that doing to the graph? Flip across the x-axis. And compression. Okay, I remember. Okay, so now we get into the add and subtract numbers. Okay, what does it generally do to the graph of a function when you subtract inside the function? Is it up, down, left, or right? I mean, we did this one in the homework last night. What was that minus 4? Right 4. So it's the same thing here, right? The only thing it changed is the graph of the parent function, but the shift is the same, right? So this is right 4. Is that one growth or decay? Growth. So if I was going to sketch that graph, it's a growth function, so I expect it to go like this, but instead of having a y-intercept of 1 now, that point is going to be moved 4 to the right. So it'll be right there. So I'm just taking the y-intercept. If that whole graph is moved 4 to the right, then the new graph looks like this. I mean, that's the only point we really knew on the graph, so just move the point that you got. All right, what is the domain of that function? Domain, all reals. Okay, what is the range? Did we change the range by moving the graph to the right? So did it move the asymptote? No. So the asymptote is still right here. You know, moving a horizontal line which goes forever to the left or the right is really no change. So you're still going to say y is greater than 0. The asymptote is still y equals 0. Okay, what kind of exponential is this? Growth or decay? Decay, because that's 1/2 to the x. Okay, what two things are going on here? What's the 20 doing and what's the plus 10 doing? Right. Stretch and up. Okay, so let's see. If I was going to sketch that graph, if it wasn't for the plus 10, what would you have said the y-intercept is? It would have been 20, right? But the whole graph has moved up 10. So the y-intercept is going to be 30, right? So 1, 2, 3, that's 30. There's the new y-intercept. If I take this graph and I move the whole thing up 10, does that change the asymptote? If you had a horizontal line and you moved it up 10, would it change the line? Yeah, it would. Remember, if you move it left and right, it stays in the same place. But if the whole graph moves up, the new asymptote is here. Y equals 10. And the graph, it's decay, so it would look like this. So what does it look like the domain of that is? All real numbers. You know, you just get it in your head. Exponentials, the domain is always all real numbers. That's not going to change. So for exponentials, this is always all reals. What is the range? Y is greater than 10, right? It's getting infinitely close to the line, y equals 10, but it can't touch that line because it's an asymptote. So the range is y values that are greater than 10, right? It's not below the line. It doesn't touch the line. It's just above the line. So a vertical shift changes the domain, or changes the range of an exponential function. Okay. Okay, so let's see, for this one, describe the shifts and come up with new domains and ranges. And if it helps, sketch the graph. Where was that one? That was that. Wasn't that? Oh, that was it. What was the shift in the first one? Left 2, right? And is it growth or decay? Yeah, it's 4 to a power, so it's going to be growth. So the only point that we've got is the y-intercept, which would have been here, but we'll move it 2 to the left, and we'll draw a function that's got the shape of a growth, right? Does moving that graph to the left 2 change the asymptote? No. This horizontal line, if you move it to the left 2, it's still in the same place. So what does that make the range? Greater than whatever the asymptote is here. Okay. How about this one? Growth or decay? It's decay, so it's going to be going down. What would the y-intercept have been if we didn't have the plus 5? It would have been 5. So what happens when you add 5? Now it's 10. So the y-intercept is here. Okay, now does moving the whole graph up 5 move the horizontal line y equals 0? Yes, it does. It's up now, it's here. Y equals 5. So just sketch in those, make something that looks like decay, goes through the y-intercept, and approaches the line y equals 5 as an asymptote. What is the range? Y is greater than 5. Right. Twenty-two. We're almost done. But I want to go back to the slide because I didn't say something I meant to say. Good. Where was it? Yeah, you know, this one, and this could get at like when we were doing the calculations and you weren't getting calculations right. A lot of times when students get something like this, 3 times 4 to the x, you end up thinking, oh, that's 12 to the x. And that's not 12 to the x. Never try to multiply those two numbers. If there's an a, that a is not being raised to the same power as the b. So don't try to combine them. Never multiply 3 times 4 to make a 12. Doesn't work that way. It's just a common place to make a mistake, especially when you look at the numbers and they're so easy, like 3 times 4. You say, hey, what's the harm? But it's a lot of harm. Okay, last. The last is, now that we know a new kind of function, we have another option for when we're modeling data. And the truth is that there are a lot of kind of processes that have exponential graphs. So you would want to do that. This is an example of one. Right? This is a table which is giving us the temperature of a cup of coffee after 0 seconds, so right away when it was cooked, and then after every 5 seconds all the way up to 30. Now you can see that it started when it was first boiled or whatever, it was 203 degrees. And then the temperature obviously is going to go down as time goes on. You know, the thing that if you ask yourself, does this seem like the kind of thing that would have an exponential graph? Well, would it be growth or decay? It's going down, so it'd be decay. The thing you have to ask if you're trying to figure out, could this be an exponential is, would it be approaching some value like an asymptote? I mean, if the temperature keeps going, can it just keep going down, or would there be a limit to how cold it could get? John? And what would it be? Yeah, whatever the room temperature is. I mean, it might get to that temperature, but it would approach that temperature like an asymptote. As a matter of fact, no, it would probably actually get to room temperature after a time, which means it would touch the asymptote. But you could see how it would start out up here, and then it would go down, 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 down. Kind of the right process to model. Now, how did we model data when we were doing it before? Because we've done this for linear, quadratic, cubic, and quartic. How did we model the data? How do you put it in the calculator? Okay, go to stat, then what? Edit, and you put the values, right? All the x values go into the L1, all the y values go into the L2. Okay, now you could very well be given this table of data and not told what kind of function it is. Yeah, if you want to put it in, go ahead and put it in. You guys don't drink coffee though, right? What? Don't you have to be 21 to drink coffee? You ever hear of people that sued because they like go into a drive-through at McDonald's and they get the really hot coffee and they put it on their lap and then the lid comes off, they spill it all over and they sue. Yeah, that's happened. So they're really careful about the temperature they give you that stuff. Now, not before. Okay, so once you get in all the data, how is it that you look at the data to tell the shape? Remember, you got to turn on the plotting of points. Where do you do that? Second, y equals, number 1, make sure that you've got on. It should be highlighted on. Mine already is, because I've done it twice today. Okay, now, once you've got that done, and you can see that it's taken the x values from the L1 and the y values from the L2, just like we want, how do I make it zoom to the data? Zoom. Zoom what? Zoom 9. 9 for stat. Zoom stat. And then you see your data and the shape of it. Does it look like it's exponential? Yeah. I mean, truthfully, if you wanted to model that, definitely would not want to do a straight line. It's probably not cubic in any way or quartic. If you did it with a parabola, with a quadratic, it would probably be a pretty close fit. It probably would. But it also looks like it's exponential. And we're doing exponential, so we'll do exponential. Yeah. I'm going to show you now. So once you've decided that you want to model it with an exponential model, right, then how do you choose the model? Where did we go? Which menu to find the kind of function? Stat, arrow over to the calc, and of course, it's not there, but scroll down, and it's the 0, exponential. So if you pick that, it's going to tell you y equals a times b to the x, which is our general form of an exponential. A equals 1.96, b equals 0.977. So just plug in for the a and the b. Is it growth or decay? I mean, by the b, we could tell by the shape of the graph it was decay, right? But the b is 0.977 less than 1, so everything matches. So that we could model with an exponential model if we wanted to. The rest of the steps are the same, right? Stat, edit, second, the stat plot, turn on, zoom 9, look at it, choose the right function. I mean, if you go to this now, let's go over to that menu one more time. So these 4 we already did, right? And now we just added the one more. Now, the number 8 is the same thing as number 4. It just switched, instead of saying AX plus B, it says A plus BX, but that's really the same thing. We just added the 0. The one we do in the next class, logarithms. Number 9 is a logarithm. So we'll actually know what that one is in the menu too. And the only other one that we might do a little bit with, at the end of the class, if we get to trigonometry, you might use that sign. Okay. So that's it. So we learned about the graphs of exponentials, growth and decay. We transformed them by multiplying, adding, subtracting, putting minus signs, in and around the function, and we did address domain on it. Domain and range. More important, range. Again, next class we'll do logarithms. Logarithms are the inverses of exponentials. What do we know about the domains and ranges of functions and their inverses? Quiet. Hey, Trevor. What do we know about the domains and ranges of functions and their inverses? They switch, right? So when we get to logarithms, since the exponential had a domain of all real numbers, the logarithms will have a range of all real numbers, right? Since the exponential had a range of y greater than equals 0, the logarithm will have a domain of x greater than equals 0, or greater than 0. Since the exponential had an asymptote at y equals 0, the logarithm will have an asymptote at x equals 0, right? Everything with the x's and the y's switches because they're inverses. And I want to take that off. Yeah. Why is that doing that? Quiet, please. You need to be working on this. Okay, you should have your book out and working on this, or I'm writing a 0 down. In a minute, I'm not done. Wait, I'm not done. Okay, and the homework, when it gets to these 4 problems in the second section, describe the transformations and try to do the domain and the range. You know what the domain is, but try to figure out whether the graph is actually of a different range. Do you really have to graph for that? Not really. I think the directions in the book just say graph. That's all it says. But try to do this. Describe the transformations, state the domain and the range.